Welcome back. I would like to discuss with you basis selection in neuroadaptive control. So I received some emails, some messages from you, and I wanted to clarify one point that is very important. It can be very important in adaptive control or neuroadaptive control applications. I will directly dive to the topic. So let's say we are looking at this delta uncertainty. I mean, in general, let's say, don't know any structure, right? We are looking at unstructured or non-parametric uncertainties. For now, let's assume X is two-dimensional. What I'm going to describe here can be applied to third, fourth, or in a high dimensional. So let's say delta depends on x1 and x2 independently. Of course, you don't know the uncertainty, but independently means, for example, you have uncertainties that x plus x to the power of 2, x to the power of 3, y to the power of u. Here, they are independent. You don't have a term that x multiplies, for example, like this. So in this case, uncertainty depends independently on x1 and x2. In this case, you can choose the basis function like we did in the previous video, meaning that you have the bias and you have an independent set of basis functions that depends on x1 and independent set of basis functions that depends on x2, where you basically RBF, radial basis function here, some width adjustment at the center adjustment to the power of 2. I probably wrote it like with absolute value in the previous videos, but since you are taking to the power of 2, absolute value doesn't matter much. Now, if you have uncertainties that are dependent x1 and x2, they depend on x1 and x2, like for example, x1 multiplied by x2 to the power of 2, x2 to the power of 2 sine of x1, I found it better to use an generalized radial basis function that depends both for x1 and x2, like in all of them. And basically, this radial basis function depends on now x1 and x2 with different centers. You can use the same width parameter here. So I would like to discuss this in this video. I am going to show you an example so that you know how we are going to choose those centers will be crystal clear. Bear with me in a couple of seconds. So in the previous video, this neuroadaptive control example, we used an uncertainty like this, and we basically use this. I am not saying this is wrong. I am saying this is a better strategy. So basically what we saw on the previous video, we started with a less number of independent radial basis functions for x1 and x2, and then we increased this number and we saw that adaptive control performance is getting better. Now, so what I want you to understand from this video, the new lecture, is that this is a better choice if you really have this cross-coupling uncertainties. And since in general you will never know the structure, so you should go with this selection. Now, as this being said, let's say if you have x1, x2, and x3, you have another term added here, and it will go on like this. So let me clarify how we are going to choose the centers. All right, this was from the previous video that I just highlighted. In addition to bias, this was the first case, right? We then increased the number of neurons and so that performance gets better. So basically we choose this our standard radial basis function. We are trying to cover the area x1 minus 2 to 2 and x2 minus 2 to 2. That's why we placed the centers. We used 5 centers at minus 2 to plus 2. Same in here for the second state. And this was the first example, the performance we obtained from the first example. And in the previous video, we showed that when we increase those neurons, we get a better and better performance. Now, I am not sharing the code. It is literally the same code. I just choose the basis functions like I just described. Each basis function depends on x1 and x2. And here we are covering the range x1 belongs to -2 to 2, x2 -2 to 2. So basically, for the first part, right, x1 is always -2, -2, -2, -2. I am covering for x2 -2, -1, 0, +1, +2. Then I am jumping to the second one, -1, and I am including every combination for x2 again, -2, -1, 0, +1, and +2. So actually basis function looks like this, right? So it is like from here, and from here. So basically x1 basically includes every combination of x2, so that if you think about like this, let's say this is x1, this is x2, this is -2 to 2, this is -2 to 2. I have basically RBF basis functions, 25 of them, to cover the entire area. Each is radial basis function that I cover this -2 to 2, -2 to 2 range and the bias term. And you can do the same. You can consider, right, this is just, instead of using this, which stands for this one, I am using every combination here for x1 and x2. So it expands my regular 5 plus 1. So basically 11 inputs to these neurons. It expands to this, becomes 5 by 5, since I consider every combination 25 and plus 1, 26. You can consider, basically you can go ahead, add more neurons to cover, for example, -2, -1.5, +1. So like you can make it more dense. That's what I'm trying to say. And in this case, the size will expand and it will give you better approximation capability, as I demonstrated in the previous video. So once you do that, basically you achieve a better performance. Compare this with this one. You have more error here. Once you fully cover this 25 of them, the area, you basically obtain a better performance, and this is the resulting W hat estimation. So I guess the punchline that I'm trying to make, one more time, this is important. You can use like this, that's okay. But in real world applications, I will strongly encourage you, if you have uncertainty and you really don't know the structure, you should, in your radial basis function, you should include all the states. Again, if you have more than 2, include another -d1j, x3 -d4j to the power of 2. It will go like this. You consider every combination like I did here. And I hope this video will be helpful for you. All right, thanks. Take care.